Okay, so hi everyone. Welcome to Systems Aging, Lecture 4, the role of chance in aging. Let's take a nice deep sigh of relief. Do our theme song. Aging, aging, aging here and there. Aging, 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 aging everywhere. Some people seem to think that old age is a disease, but research shows that senior citizens are more at ease. Subjective well-being is at its max, and your brain is wiser, and you don't have to tolerate your PhD advisor. Aging, aging, aging here and there. Aging, 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 aging everywhere. Aging, 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 aging everywhere. Aging. How many of you have a PhD advisor? How many of you are master students? See, young people are interested in aging. How many of you are, look, Sami, look, how many of you guys are first year or master students? How many are PhD? How many are postdocs? How many are professors? So you see, the young people are interested in aging. The younger they are, the more interested in aging. How do you explain that, Sami? Why is that? Why are young people interested in aging? Welcome. Okay, so we say welcome, breath, song. Okay, so we're in lecture 4, right? And let's look at the arc of the course. Arc of the course. We started with the patterns of aging, like the Gompertz law, where the risk of death doubles every 8 years, right? This lecture, we're going to get that law from molecular parameters. It's a very exciting moment. Then we talked about the molecular hallmarks, and we said that this circle, smooth and inoffensive of hallmarks, we're going to order into circuits. And the circuits are something like this. There's things that happen in the cell, then on the level of the cell, and then on the level of the whole body. So in the cell, we talked about two kinds of pathways of damage, right? One is DNA histone acetylation that leads to opening of places in the DNA that had better be closed, like telomeres. And that causes double-stranded breaks in areas that are hard to repair. That's one path. Another path is kind of protein aggregates that, for some reason, accumulate in the mitochondria and cause all kind of trouble. So both of these things, so these are two ways, actually there's at least two ways to age. And later I'll talk about one is probably for the body, the other one for the brain. In yeast, that's all there is, only this thing. You still age. They cause damage, right? So we talked about damage. In order to have a difference between age 20 and age 80, you need something to accumulate in your body and stay in it, right? It can't be a skin cell that's removed after 30 days or a gut cell removed after 7 days. So what kind of cells stay in your body? We talked about neurons and things like that. So here, this screws up neurons. And this part is important in dividing cells because it's DNA. So cells that stay in our body are the stem cells. And most of them are fine, but once in a while when they have this damage, they can tolerate it, they divide very quickly, but they pass on their chromatin state to the daughters. So stem cells are in our body all the time, they divide, let's say, once a few months, and then they make cells like skin cells, let's say, they divide very quickly. Let's say 20 divisions, that's 2 to the power 20, is a million cells for each stem cell division. And then they climb up and they become skin cells. So they produce damaged cells that become senescent cells. Senescent cells. And they secrete their senescence-associated secretion profile to cause inflammation and to cause stem cell exhaustion or reduced regeneration, or wounds take longer to heal, all these things. And these things cause the decline and disease, and death, in ways that are very individual. So diseases you get is very genetic and very environmental. So we have this, like I promised you, we took that circle of hallmarks and we open it up into two circuits. This leads to dementia, neurodegeneration. We'll have a whole lecture on neurodegeneration, Alzheimer's disease, delicious things like that. We're going to focus on this side here, which is neck down. So, and when we think about interventions, there's different things we could do in each of these levels. And then we started talking about a model, a mathematical model, to connect this and this. Because these are two fields of study. This is called demographics, counting deaths, counting disease, epidemiology. This is called molecular biology of aging. We want to connect them. Why? Because when you connect something, you use the power of both fields. So in molecular biology, people don't think about this. And here, people don't think about this, usually. Of course, there are people who think about it. And we're going to connect and have a great power. Like, for example, based on this, I can tell you what I think is the DNA acetylation specifically that is responsible here. Because to pick a needle out of a haystack, you need some mathematical properties of it. So that's going to be in the future. So where are we going? So this is the second lecture where we talk about our saturating removal model, or the model of houses, garbage, and trucks. So last time we talked about that model. There was a village, houses, and they make garbage. This village has 100 garbage trucks, and they're perfectly capable of taking care of the garbage. But more and more houses are built. Now it's a big city. We're not evolved to be old. This village was not evolved to be a city. It still has only 100 trucks. What happens to the trucks? They're overloaded. Garbage piles up in the street. If the trucks go on strike, there's even more in the street. Before long, the garbage reaches a critical level of stinkiness where it's impossible to live there anymore. At the threshold. And there's noise. The noise is like trucks going on strike. This is saturating removal model. Let's think about it in the molecular terms. What are these houses, trucks, etc.? So the garbage, which we call X, is in our framework. Okay? And this model is agnostic to what the damage is. That's why it can fit yeast, which has no senescent cells. It can fit E. coli, it can fit worms, flies, humans. Each time it's a different damage. And in fact, there's a whole hierarchy of damage. So maybe if you treat the damage you died from first, you reveal the next damage. So if we treat cancer, diabetes, we're going to get Alzheimer's. If we treat that, we're going to get to the next garbage, which is, who knows? Do you have a guess what it is? No? So what are the houses here? So if this is X, if senescent cell amounts in the body, again, with all the caveats that it's an emerging field, senescent cells are very heterogeneous. In different organs, they secrete different things. It's hard to count them in vivo, but we're going to make the approximation total body senescence for us, which is, I think, like a consensus right now for many researchers, but not everyone. Everything up till here, this is the houses. Why? Because this stuff rises and accumulates with age. Why? Because the chance to get a defective stem cell that gives rise to defective differentiated cells, it's a rare process. And you need that defect not to harm the stem cell itself, otherwise it gets competed out by other stem cells. And something that when it transmits to the daughter cells, they divide, they get DNA damage, they get in trouble. They get senescent. So you need that, and that's rare. So you have, when you're young, you have one here, then another, and they stay in the body. Another. You can't remove them because they themselves are not damaged. Another. Make a column of garbage above them. See what I mean? And now you're old. You have, and your body, the beautiful senescent cells that are good for wound healing, are now taken outside of their design constraints, and they fill your body with inflammatory signals and stem cell exhaustion signals, which drive, as we'll see, all the four horsemen, and et cetera, et cetera. Okay, so that means that the accumulation, the telomere opening, double-stranded breaks, even things here, because this damaged cell might be able to repair itself somehow. That repair enzymes, all this autophagy, everything is in the houses. So if you do caloric restriction, the houses go to repair because they think they're starved, they recycle. It's all in the houses. And the trucks are things that remove the garbage. So in human beings, it's the immune system, like NK cells, macrophages. These are innate cells whose job is to remove damaged cells. How do they do that? Damaged cells are programmed to present things on their surface that NK cells recognize and kill you. That's normal. And macrophages clear up the debris. But they have other jobs. They, for instance, kill cancer cells. They kill virus-infected cells. They clear the debris, amyloid debris, et cetera, et cetera. And you do have a finite number of these. With age, the number of these trucks doesn't grow. They look more exhausted with age. That's like, I think that's the trucks here. So this course is integrating a lot of stuff. That's why one of you told me there's a lot of threads, but I promise you we're going to tie up all the threads. But I keep repeating it so that slowly we all get it. And those are the houses. And the X critical has to do with, the threshold has to do with somewhere here. When you can't tolerate anymore this massive push on your physiology. Now, how many senescent cells do you need in order to make somebody really feel bad? That is to say, their secretion is in the blood and affects all organs to a level that's really bad for your physiology. So the answer that if you have a cell that really wants to secrete stuff, you only need 1 in 10,000 of your cells to secrete stuff in order to affect the whole body. For example, thyroid cells, 10-gram organ, 100-kilo person, 10 to the minus 4, they affect everything. Same thing with the adrenal. So 1 in 10,000, 1 in 1,000 cells is enough. So now where are we going in this course? Today we're going to talk about the noise, the randomness. Very interesting. The question of why is it that you take genetically identical mice in the same conditions? They're twins. They die at different times. What's going on here? And get to this law, which of course means people die at different times. It's not like 0% incidence, 100%. It's not like that. Except in science fiction, like in Star Trek had an episode like that, where at a certain age you go check into a machine and it kills you. All right, so and where are we going? So we're going to talk about how this picture, we're going to talk about the horsemen and what you can do about them, cardiovascular, metabolic, neurodegeneration, and what? Diabetes, heart attacks, cancer. Then we talk about decline, what you can do about your VO2 max, your linear decline of abilities, and exponential rise of diseases. Right? And why are these diseases age-related? Why is the chance of getting cancer at 20 and 80 is like 400 times more? It's the main risk factor. So we'll talk about horsemen, decline, what you can do about it. We'll talk about exercise, nutrition, sleep, all these things, how they connect. The social, emotional well-being, how they connect. And the cutting edge, like what's the cutting edge approaches to slow aging, extend the health span. That's our course. What do you think? Yeah. Yes. Let's do. Where should we do that? Everywhere, right? Here. Yeah. There are differences. We'll talk about that. And if I don't talk about them, you should ask. Do you know that females live longer? By how much? 5 years. Few years. So yeah, there's a lot of emerging research that lots of interventions work only in males or only in females. For example, well, I'll talk about some today even. They only work in males. Yeah, and then figure out why. And I mean, I say this course is about the cutting edge topic, so we don't know all the answers. I don't know all the answers. So some of your questions, they'll say, I don't know. Maybe you can find out. I meant you there. Okay, so that's the arc of the course. Review. Yeah, you see?
Yeah. The number of NKs and macrophages is not a constant in life, right? If you have a disease, it will increase. So it gets to the limit at some point.
Yeah, so you're asking.
And why is there a limit? Yeah.
Yeah, so each of these blood cells has its own feedback loops to regulate its size. So NK cells have a very interesting regulatory loop. In the blood, they have a half-life of a few hours, and that's what we can measure, seeing them right. When they get into the tissue, their job is to massage cells and look for damaged cells and kill them, inject poison. They're like, so in order, their number is regulated actually by their function. So in order to survive, they need to massage cells, and the cells in our body, a lot of them make this growth, or it's a elixir of life for them. It's called IL-15. And only when they touch them, it has to be physical touch, they get this IL-15 and they can survive. And they can survive in the body for years. Once in a while, they go out of the blood, into the blood, then a new blood cell quickly takes their place, and so their number in the tissues is quite strictly regulated just by the volume of tissue you have. Did I answer your question?
But like, if now I have, let's say, a start of a cancer,
Yeah.
which you said that they should kill,
Yeah.
I would expect them to, I don't know, send a feedback loop to the bone marrow, create more NKs, macrophages.
Yeah, they might do that. They might send a feedback to make more NK macrophages. Then the NK cells will be made, they'll get into the tissue, and they won't be able to survive because all the space is taken. Only if there's more space. In macrophages, also monocytes, they do rise with age a little bit. There's something called myeloid shift, but it's not enough. It's not from 100 trucks to 200 trucks to 1,000 trucks. It's from 100 to 120 trucks. So there is some inflammation. The body knows it needs to repair, but there's a limit. There is a limit. Your blood can only take 50% of its volume of blood cells. 90% of that are red blood cells, just to breathe. And the rest is white blood cells. And there's a limit in the blood, but also I mean, they can rise, but it's not enough. In fact, if you have a source of garbage where the trucks get a feedback signal and they rise to levels sufficient to reduce it, it can't be a driver of aging. So the driver of aging is something that increases and trucks reach capacity. If they don't reach capacity, it keeps the garbage low. It's not. Did I explain myself?
Yeah, it raises more questions.
Yeah, of course. No, it's really a very important point. All right, so here we're going to review. I want to test your understanding of this truck model by telling you something, and I want you to explain it to me from this truck model. Okay? And the way you're going to do it is to pair with each other and see if you can understand it. Here's the experiment done in 1970 and repeated many times. It's called heterochronic parabiosis. You take two rodents and you stitch them up so that when you cut them and put them together, their blood vessels unite. So they have shared circulation. Their blood is flowing together. Now you take an old mouse and a young mouse and connect them. And the shocking result was that the young mouse gets a little older and the old mouse gets younger. Or rat. I'll say it again. You connect their circulation, the young mouse gets older, the old mouse gets younger. Now, I don't want anyone to be alone here. You have to find someone behind you or near you. Explain that using the truck model. No, just pair and share. Pair and share. Parent share. Parent share. Parent share. Yeah, together you can. Okay. Who wants to try to explain it? Who wants to explain it? Who wants to explain it? Wants to explain it? So a very simple explanation. Yeah. Yeah. Sorry.
Well, a combination of lot of vessels means that we have more houses and more trucks. So the trucks go to the outer neighborhood where there's an overload of trucks. That's why the older rat gets a tad younger. And because the younger rat has less trucks for himself, then he gets a little older.
So the answer is, like you say, it's the city and the village make a union and share the trucks through the blood because trucks are immune system cells go to the truck, and therefore the trucks help the city reduce garbage, but the garbage in the village rises. And there's just from the amount the senescent cells rise, you can actually show that it has to be something like this model in terms of damage rising and removal saturating, just from those numbers. That's a paper by Corinne 2020 about hydrochronic parabiosis. And what happens when I separate these creatures? What's going to happen?
They're going to go back to the way they were.
Back to the way they were. That's what happens after 2 months. When you take, here's another question: I transplant a heart from a young person into an old person. What's going to happen to the person? What's going to happen to the heart? Yeah. What's the answer?
Not sure.
Yeah. Good. Thanks for saying. It's very good to say not sure. Who wants to guess? It's okay to be wrong. Yeah.
Hopefully they survive the surgery.
Yeah.
Then they'll continue living, but the heart will probably age a little bit, like if we're just looking.
Yeah. So the majority determines, so the heart will get older more than the person will get younger. Because the amount of garbage and trucks in the heart is like this, a heart, right? No, is it?
Yeah.
It's pretty impressive, no? It's like 1 billion beats per lifetime. Okay, yeah. Just 2? Okay. I didn't say it's the only model that fits. Yeah, go on. Yeah. So the question is, when we separate them, maybe the trucks will stay. And good point. If you want to think about it more, read that paper. And okay. So we did parent share. Look, we're zooming right across, right? Okay, so I want to talk now about this question is, why do genetically identical organisms die at different times? And what does that mean? And also identical human twins, like the Swedish twin cohort. If you take twins that, you pass the time when they die of extrinsic mortality, like twins over 40 or something, and you look at these identical twins versus non-identical twins. which grew up in the same house but have different DNA. Right? There's identical twins, monozygotic, monozygotic, dizygotic. The amount that genetics determines lifespan is estimated around 20%. That's not a lot of variation in life. So it's not particularly genetics. In genetically identical organisms, it's not genetics. And it's not environment, as far as you can tell, because they developed in the same womb, and they grew up in the same social economic status, more or less. And the mice really live in the same cages. And the worms and the yeast, and all the organisms have this issue. So it's not environment. What is it? And a lot of times you see that in biology. And it's rare when you can explain it, but we're going to do that. Try to do that. So this is the stochastic. Stochastic means like random, but not chaotic because there's some rules to it. Yeah. So it's not genetics. It's not environment. It's what we're going to call noise. Or noise. And one line of thinking where biologists have thought about this very deeply. This is work by Fit. There's a book called Development, Aging, and Chance, or something like that, from 2000. Is maybe its initial conditions. This is something like from your genes in the same womb, but when you develop, your body is different. So if you look at your hands and you look at these blood vessels here and here, you have the same genes and they form your body in the same body, but if you look at it, you see that the patterns are different. Right? You see it? This pattern, this pattern. No? You have the same? Exactly, we're not symmetrical. Yeah, we're not symmetrical. But everything has a stochastic component when you develop. Your genes, so maybe something like that. Maybe some people are born more frail. Maybe even the twins. One is born more frail. And of course, there are people born more frail, like people with germline diseases or diseases getting injured or stuff like that. So something about the initial condition. The whole book is about things where chance can affect development, can affect your brain, can affect your... There's no doubt, like your fingerprints are... The identical twins don't have identical fingerprints. So there's a random transformation between genes and shape, phenotype. But it seems unlikely that that's the main reason for lots of reasons. But one of the main reasons is that if you look at those twins, their health status it's not like parallel, it's like this. See what I think? It's not like deterministic from the initial condition to death. It's like a lot of changes. And the best measurements we have, so in order to characterize the noise, I'm going to talk about 3 different experiments. It's rare in aging research to follow the same individual over time. There's a lot of cross-sectional, which means you take a population and you look at them. It's rare to follow the same individual over time. Actually, the best data is in humans, probably, where you have health records. But there's 3 gold standard experiments where you measure or actually 2 experiments where you measure the damage, something like the damage X over time. We need that in order to understand things like, does the initial condition affect your damage later, because we need to follow the same individual over time, right? I hope I'm clear. So I mentioned them before. One is senescent cells in mice. If you remember, the mice that make light, make photons out of P16 promoter. And every 8 weeks, for 33 weeks, and you get these trajectories that cross each other. And at old age, there's more senescent cells than at young age, but some old have similar senescent cells to the young, according to this measure. And the other one is in a single-celled organism, E. coli, that's starving, and you use a dye that only goes in when there's a hole in the membrane, that's the damage. It goes into the DNA and becomes fluorescent. Then you measure fluorescence, or the rate of accumulation of fluorescence. That's actually it's the membrane potential. It's exponential to the membrane potential. It's a way to measure damage. And you have here 600 E. coli cells, and it's the damage. And again, they cross each other in old age, which is 100 hours of starvation. They have same property. Okay? They become different from each other. Damage rises. And then there's also the human, which is not exactly damage, but we like to think of it as a proxy, which is called the frailty index. As I told you, it's a list of conditions. Some of them are trivial, like backache. Some of them are dangerous, like cancer, being able to do dress in the morning. Just enough of them. And each one is 1 or 0 at each age, and you average. So you get a number between 0 and 1. And usually you can't, life is not compatible with being above something like 0.6. Why somebody is a backache and cancer the same? It's not the same, but it's a very good predictor of, probably the best predictor of mortality and stuff like that. And again, same situation. If you follow people, you get the same statistics. And I'll tell you what I mean the same statistics, because we want to talk about noise. So we want to characterize what the noise looks like, right? So there's like distributions and stuff like that. So if I look at the mean is a function of age. In all of them, it rises like this. And if I look at the standard deviation, which is the difference, it also rises. But if I look at the relative width, which is called standard deviation divided by mean, this has an important name in statistics, coefficient of variation. Hope many of you heard about this. It's standard deviation in units of the mean. So it's like in percents, like how much percent they vary. Because standard deviation goes slower than the mean, it looks like this. And in fact, 1 over CV rises with age. More about linearly. In all of these three. So this is different organisms. E. coli and mice for sure have different X, because mice don't have senescent cells. They don't have an immune system. They don't have diabetes. They don't have PhD advisors. They're simple. But the same thing. And then I can also talk about the distribution. So if I look here and ask, what's the probability at a certain age to have some damage? So when you're young, it looks like this. So most people have very low damage, most individuals. And with age, it grows like this. So it's right skewed, which means the most probable health. There's some people with much worse health. And then with age, it flies to higher damage. It becomes more symmetrical. So skewness, function of age, goes down. So I'm telling you all these statistical stuff because, of course, we're going to get them from our model, miraculously. This is my wife. I put in very relaxing music because stress is not so good for aging. And we'll talk about why. It's an immunosuppressant. Stress reduces your trucks. You know that? Cortisol, is it like steroid, corticosteroids you take as an immunosuppressant? They're analogs of the stress hormone cortisol. It suppresses your trucks. Did you know that? Chronic stress. Well, you should know that. That's why you came to this course, right? To know like life-saving tips like that. But just to tell her that I'm teaching. So you guys won't be stressed. What do you think? Was that nice music?
Yeah.
I'll ask her to call again. Okay. She gave me... All right. Yeah, I want you to edit that out, okay? Okay. And what else can we say? Oh, yeah. All this stuff you can get from cross-sectional. But if you look at longitudinal, you also see something very interesting. Age, X. When you're young, the fluctuations are fast. When you're old, the fluctuations are slow. So if you're unlucky enough to be above average, X, you stay that way longer the older you are. Why is that? It has to do with the trucks being overloaded, so that their rate of removal per unit garbage is lower. And it sticks around for more time. But okay, that's an experimental fact. So this is called it's called slowing down, critical slowing down, or increasing autocorrelation function if you want to do that in physics. So these are the facts, you can say, the facts of noise.
Can you repeat them again for a second? Sorry, just like quickly, briefly.
Yeah, so rising mean and standard deviation, but reducing relative heterogeneity, CV. So this is very weird because most things you measure about old people become more and more different. Blood glucose is different because some people have diabetes. Kidney functions are very different because some people have kidney disease. And whatever you want. Most things become, also their CV grows. But we're looking for something where we become more similar between old individuals in relative terms. And that, you can say, of course, only after the fact we saw the data and then the model. But now that, like after a long time, I can say that maybe that's even a priori a property of the driver of aging that's upstream of all the diseases. Because the diseases are individual, genetic, environmental, like you're eating a lot, obese, insulin resistant. The same level of X will give you type 2 diabetes. Or if you have genes like ApoB, the same level of X will give you coronary heart disease or stroke. But if you want something that's upstream, it should be more and more similar between old people.
Isn't it kind of like going down the slope of a mountain? There's like 100 ways for me to get there, but the bottom is the bottom. You know, or the top is the top. Like.
Could be, yeah. Okay, so and then
Is that like sufficiently vague?
right skewed distributions that become more symmetric, and things slow down with age. Fluctuations slow down with age. Meaning the damage at young ages doesn't predict anything. Close to death, damage is going to predict a lot. Let's take a nice deep sigh of relief. We talked about initial conditions, white noise, CV and skewness. Good time for a break. Okay. If these statistical facts of noise were a bit too fast, I'm going to come back to them again and explain them again. There was something that I want to clarify about the biological scheme. So, according to, I would say our best guess is that you can say that the stem cells don't have this usually problem with telomeres because they have an enzyme that extends telomeres. The problem with the stem cells is here. If they have altered epigenetics that we think is insulin-acetylation, and you learn why in further lectures. That's not damage exactly. It's like information error. Some people call it information theory of aging. It's for instance, if there's DNA damage and you can repair it, those marks sometimes move, and there's no way to really reset them. So that's an entropic thing that happens slowly over time. And those stem cells, they're not damaged. If they are damaged, they either repair themselves or removed from the pool, and then we don't care about them for aging because we want something that lasts decades. But the cells they make, those alterations cause bad things to happen because their telomeres, now they divide a lot of times, their telomeres can shorten. They no longer have that enzyme telomerase because that's a defense against cancer. Cancers don't have telomerase. If they divide, they stop dividing because their telomeres get shorter. A A lot of cancers have a mutation that upregulates telomerase, like because of that. So in these cells, you have this stuff. This stuff can also happen in any cell, but as I said, cells that are transient, we don't care about. We care about the cells that stay in the body for decades. You can think about this is altered stem cells. This is what happens in the damaged differentiated cells. And a lot of them can repair. They can repair. But if they don't repair, they become signal the immune system, etc. So that's another layer of detail maybe about houses. The houses have some parts in them. Houses have some structure inside of them. Okay. What I want to do now is to talk about noise in the saturated removal model, in the houses and truck model. And what I want to do, my goal is to show you how this model with the noise gets all of these features and the Gompertz law of death and all that stuff. So why do genetically identical organisms die at different times? In order to do that, I'm going to do some math here. And I want to tell you that this math is going to be, first of all, understandable using a geometric construction, which is a ball running down a bowl. So everyone can understand. That it's all going to be in the lecture notes because they're very detailed. How many of you have looked at the lecture notes? Oh, great. That some of you might not care about the math and just want to understand biological mechanisms, and others might care a lot about the math. So in our exercise, we're going to have an option. You can do a math thing like this, or a biology mechanism thing, or if you want to challenge yourself, do both. It's okay. It's no premium, but anyway, the math is elegant, and I love it. So the idea is going to be like this. We have our stochastic differential equation, which means an equation with noise. So it's the rate of change of damage is at a t. These are the houses rising. As you recall, what actually happens is there's a source of damage that's not removed. These things whose number rises linearly with age, and they produce the garbage because you have these garbage-producing units, the houses all over. And then there's the truck saturate. So remember, that's this equation, where the trucks at high damage, they reach a maximal removal rate of beta. Talked about that last time. The truck saturate, as Michaelis mentioned. And now we're going to add noise. So noise. What is noise? So there's different ways to add noise, but the simplest way, and the thing that works, is just to generate a random number every time step. Add it to the equation. There's a slight technical thing. You'll see maybe in the exercise that when you do that, you have to take care that your time step in the simulation is delta t for this and square root of delta t for this because it's a random walk. I'm saying that because it's like when you solve it numerically, there's a technical detail, but in principle, it's like adding a random number each time step. So adding garbage or removing garbage. What can this be biologically? Is a big mystery, but we'd love to know. But there's some candidates. Okay? So it's something that we think it has to do not with the production of the irremovable stem cells, because that happens. There's so many millions of them that it's like a lot of stochastic events, and that noise in there is very, very small because it's so many events. We think it's coordinated strikes in the trucks. The trucks go on strike. Your immune system works more and less, and more and less, and more and less. We also know that because of some very interesting phenomenon where a dimensionless number, which is truck speed divided by noise, is about 1 in organisms is different as human, mice, worms. That's incredible. So we think noise and trucks are connected. Whereas things like the house production rate in humans gives you decades, in mice gives you years, in flies gives you months, in worms gives you weeks, in E. coli gives you hours. It's very different. Trucks, by the way, in mice, we know, work at a speed of when they're fastest, like when you're young, the lifetime of a piece of garbage is 5 days, and when they're old, it's 1 month. And that's what you expect from saturating. And that's the experiment we did with Valery Krzyzanowski, because that was a prediction of the theory. If the trucks get overloaded, each piece of garbage should stay around longer when you're old. And the way Valery did that experiment is by letting the mice breathe a poison called bleomycin. It causes DNA damage, and after 5 days, the whole lung is senescent. And not a whole lung, but there's tons of senescence. The mice survive this, and then you kill them at different points, and take out the lung, and ask. This is biology. We're trying to save human lives, and ask what fraction of the lung cells are senescent. Right? So you increase senescence, and then the trucks removes it. So if it removes quickly, the half-life is fast, and if it's removed slowly, the half-life. And that's how you got 5 days and 30 days, which is exactly what you expect from the parameters fit this completely different data, just the senescent cells. So that was like pretty incredible. But so anyway, what could this be in our biological picture? So what affects the immune system globally? So one thing is sleep, because last time we sang the song "Roll, Truck, You Roll" all night long, because the immune system does different things in day and night, and at night it does more maintenance. Fluctuation in sleep. What else? Stress. I told you that cortisol is immunosuppressant. So chronic stress, gonna stop the trucks, slow them down. Okay. What else? Infection, because these cells are, when the body has infection signals, these cells, the trucks go basically to fight the infection. Not all the cells, but they act differently. So infection. So these things fluctuate. So that's one possibility. So we don't know, right? That's one of the big unknowns for us. How important these factors are in noise. So we use this white noise term, which is add a random number, mean 0 and standard deviation epsilon from a normal distribution times square root of delta t. Okay. Amazingly, there's a way to solve some things about this stochastic differential thing. And it was this kind of equations were developed to analyze Brownian motion. We have like a particle, being hit, or diffusion. It's kind of diffusion equation. And the way you do that, and I want to do that because for me it's joyful, is to transform this to an analogous picture, which is a particle in a bowl or a potential well, and it's rolling down the potential well, and at the bottom of the potential well it's at equilibrium, and all the time this potential well is like, this bowl is like on a truck or something, different kind of truck, and it kind of randomizes the bowl position. Because it's like a particle in a potential well. And what I'm going to show you now is that when you're young, the bowl is really narrow and slender. And as you all age, this part of it starts opening, like this. So the position of the steady state moves and accelerates. And because the bowl is shallower, the fluctuation is going to be bigger. Standard deviation is going to rise. And because only this part is opening, it's skewed to the right. The ball is more sampling that part. And the beautiful thing we're going to see is that this ball kind of opens up kind of gradually, linearly with age. But then the possibility of falling over a cliff and dying goes up exponentially. Because just like in a potential delta G that goes down linearly with age, e to the delta G exponential. And so because the chance of noise making you climb up a steep is exponentially more unlikely than making it roll down a narrow plane. So that's how a linear becomes exponential. I'm going to show that. That's how you get the Gompertz law. So what is this bowl I'm talking about? All right. So the way in general to solve equations like this is to think of a potential function. Now this might be quick for some of you, so let's just do it, and you can look at the lecture notes. If this is we call this velocity, this thing, then we want a potential such that its derivative equals the velocity. So what does that mean? The derivative means the slope. The slope here is production minus removal. What function, when you take its derivative, gives you this? You can solve it. It's this function. It happens to be true if you take the derivative. For instance, log is 1 over k plus x, and the beta here gives you x over k plus x. All right. This function looks like this, what I drew. When you're young, this minus eta t here opens up this thing. Opens up over, like, linearly with time. And this side, the left side comes from this beta k thing. Doesn't change with age. So it's like, it's a hard wall here and a soft wall here. That's what you get. All right. You can calculate now the distribution. So here, at any point here, I can say this is changing really slowly. So I'm going to assume that we're steady state on the time of the trucks, like quasi-steady state, and see the distribution. And the distribution, the P of x, the chance to have so much damage, actually goes like this. This is, you should all remember, like Boltzmann distribution. It's like I said, like an enzyme where this is similar to temperature, noise, and this is like the delta G. So the probability to be far away from the steady state is very small if the potential is big. So you can calculate what P of x is. Something like this. Distributions that look like this. So from this analysis, you can get this. All of these facts follow from this distribution: the standard deviation, the skewness, even the critical slowing down, because when the bowl is very wide, when you're far away, the restoring force is so small, so weak, it takes a long time to return. If the bowl is like this, when you're young, if you're far away, you roll quickly. So that's why when you're young, noise, so if you're above average when you're young, after 2 weeks, you're below average. If you're above average when you're old, stay there for months. This is just an analogy, but you can solve everything. To sweeten the pill, I don't want to talk about stochastic aging, although it's hurting me. still a mystery. You see, when I was very young, my bowl was slim and slender. Now that I'm more old, my right slope's getting cold. The gods, they throw their dice, their eyes as cold as ice. And someone way down here loses someone dear. I don't want to talk. Okay, enough of that. Armed with this machinery, we can now understand why does risk of death rise exponentially with age, the Gompertz law. And I just want to say that experimentally, it rises exponentially with age, and always in all organisms it slows down at very old ages, the risk of death. So above 800, it's about 50% per year in humans. In mice, it's even like before that it starts slowing down. Before that, in relative terms, it's more like what's called Weibull distribution, which is Gompertz and then turns into a power law. So when you do a simulation of this model, damage is a function of time, and you do those random numbers, one individual has damage like this. And another genetically identical individual in the same parameters have different random numbers in the simulation. So, like this. And another one like this. Right? Because we have add random numbers to the situation. And the thing is, when you're old, the trucks are really overloaded. So if they put a piece of garbage, it'll take the trucks a long time to get to it. So noise has, when you're old, has more time, you can say, to randomize things and to actually have a catastrophe when it adds a lot of damage before the trucks can get to it. So at old age, the noise is kind of amplified, you can say. Yeah? And your amount of garbage you have is pretty high already. So we're going to model death in a way that we can compute with. It's just an approximation, is that there is a threshold for death, which means that when damage exceeds a number, this person dies here, this one dies here, this one dies here. Genetically identical individuals die at different times. We don't really know the relation between senescent cells and risk of death. It could, what I'm going to say here also works if you assume some kind of function. It doesn't have to be step function, but a lot of things you can understand just by making the approximation. There's a death threshold. Okay. Indeed, in experiments like this, you don't find individuals alive with damage above a certain threshold, like bacteria or mice or, yeah.
Two questions. You drew the slowing down of X.
Yeah.
And the x-axis is still the age.
Yeah, so this is like time, let's say. This is when you're young. This is when you're old.
So it seems like it's the same axis, so I would expect.
Yeah, so if I drew this more accurately, it would look like. Thank you. Yeah.
Second question, is the white noise damage can be also negative in this model?
Yeah. So in this model, you can add or remove. Usually that's not a problem because x, of course, you don't want x to be negative. By time t equals 0, you can have a mistake where the computer goes to negative. So in the simulations, you can add a wall there saying, no way to do that. But that makes a very small difference because what happens when you're young doesn't really affect, as I said, because of this rapid time scale.
But in older age, the damage stays longer, so your hair can also stay longer?
At old age, you can see in the data, damage can go down. So it goes up and down. It doesn't always just go up like that. That's very important. So that's, you see that experimentally, and you can also. The thing is that it goes up and down more slowly than in the young ages because the trucks are so slow. The lifetime per piece of garbage is longer because the trucks are so overloaded. Make sense? Or did I explain this? Okay. So what's going on here is that you have this x critical here. That's the cliff, you can say, that I drew before. No, x critical. This is x here. Anyway, there's x critical. That's the cliff. And like I said, in order to reach it, look what it has to do. The noise kind of kicks you, right? In order to reach it before the trucks get you, you have to go a lot of noise steps to fall over the cliff. Now, since noise can be right or left, it's like flipping a coin and getting heads many times. The chance of doing that is very small. It's 1/2 times 1/2. In other words, exponentially small. If I now open up you need less steps to get there. I mean, now your bottom of the bowl is here. You need less steps to get there. So it's like I'm removing coin. And when you're young, you need 10 flips. Then you need 9 flips. Then you need 8 flips. Then you need 7. So that gives you an exponential. And so this is what's called crossing a threshold. So when x greater than x critical, this is called first passage time problem. So you have this stochastic process. What's the first time? It's like a gambler. Like how long it will take to get more than $1,000 or lose all your money. That's like a first passage time problem. And again, you can calculate it. And this first passage time problem, which is actually the risk of death, is the potential at x critical minus the potential at your average divided by temperature. That's called Cramer's law in physics. And it's just very simple. It means the potential difference, the smaller the potential difference, the less number of steps you need. Okay? So I might have drawn this wrong, but this is right. And then when you do that, you take this potential. The only thing that has to do with time is this. You get that this is, and you can even get what the Gompert slope is, eta x critical divided by epsilon. And so you connect this slope, this everything, this h0, this slope, to molecular parameters like production rate of houses, noise, death threshold. Why noise similar to temperature? It's just an analogy, but temperature is something randomizing, and noise is something randomizing. The same mathematics. It's not real temperature. It's like, of course, if you lower temperature, invertebrates that don't keep their body temperature live longer, unless you go very cold.
How did you get the Boltzmann statistics?
This is the Boltzmann statistics is like saying that in order to be far away from your steady state, you have to throw the coin enough times. How many times? You want to reach a certain distance, u, and steps of size epsilon. And so that's why it becomes increasingly unlikely to be far away. The potential is high.
No, I mean, like, why is it Boltzmann?
It's like Boltzmann. The same in Boltzmann, it's minus delta G over KT, right?
Yes.
But it's analogous to Boltzmann. It's just like in Boltzmann, you don't find a particle far away from its average because the temperature has to do a lot of unlikely things to get there. It's exponentially rare. Same thing here. The noise has to do a series of unlikely things. So you get the same math. I want to use Boltzmann because I know a lot of biologists learn about. So you think of an enzyme that has a delta G, and you have some reaction rate. Now I'm going to lower that delta G. the reaction is going to go faster. Going to lower it some more. Reaction is going to go faster. Same thing here. That bowl opening, I'm lowering the delta G linearly with time, and that becomes an exponential risk of crossing that threshold. So that's how a linear process becomes an exponential process. And the linear becomes because of the rate of production of the houses, which is, in the end, this stuff comes from entropy, comes from random, slow, rare events where you rearrange the histone, acetylations, and things like that. And that's entropy.
Does it has to do something with the system being in equilibrium?
System's out of equilibrium.
Out of equilibrium.
But here, to get this assumption, you need this separation of timescales. The bowl is opening much more slowly than the trucks are working, and there it's like equilibrium. Exactly, yeah. It's like an equilibrium. It is. Yeah. Of course, biology is out of equilibrium, but we have this separation of timescales that houses are built much more slowly than garbage is made and removed. That's another interesting thing about aging. So you have this two timescales, right? Over decades, and then you can have this fast shifts. So I think this is a good place to do parent share. So you can work with this concept by asking somebody who it's best if you have people from different backgrounds, like biology, computation, right? So why don't you, let's spend a few minutes, find someone from a different background near you, and talk about this concept of bowl, noise, first passage time. Please. Choose. I want to hear global. מה שלומך? סורי. זה קטע קצת קשה לסטודנטים. מה שלומך? היית בחוץ לארץ. איפה היית? נשימה? כן. כן. פגשת אותו היום? אני יכול להכיר ביניהם אם אתה רוצה. תשלח לי אימייל, אני אחבר. I don't want to talk about stochastic aging, though it's killing me. All right, so any questions came up that you want to, yeah.
I get the view is like it's nice equivalent to potential in thermodynamics, but what does it mean like biologically? Like the potential of death? Is the probability of death? Or?
Its potential has to do with the relative strength of production and removal. So that it's a function where the slope is production minus removal. So at the bottom, where the slope is zero, because the derivative is zero at a minimum, as we recall from high school, production equals removal, and the bottom is therefore the steady state. So it's very easy to understand if you think about it. So it's like potential is, what is it? It's like a energy that can be transformed into force. Its derivative is force. So the force here is production minus removal. Yeah. Yeah.
It seems that I want to ask a question. It seems to me that when you're older, then the slope is not very steep. So the meaning of not getting like worse right now, just like staying the same, like in order to kill you, it's not like it's not that bad for the killing part. Like you're not going to get any better. So like from the randomness, yeah, I think it's supposed to be like maybe a big deal because now I don't have only to choose like kill, 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 kill. I can also choose like don't like kill, kill, don't do anything,
Exactly.
don't do anything, don't do anything, kill,
Yeah,
kill.
and you still die.
Yeah.
That's why it's exponentially more likely.
Yeah, but you also have like more options. You don't only need to kill, kill. You also get the other option of do nothing.
Right. So all these are computed in this. This is exactly where you get this function. Yeah. So like you're young. When I was young, my bowl was slim and slender, but now that I'm old, the right side's getting cold. So if this is x critical, I have to do a lot of work to. But here now, this is my steady state. Don't need to do a lot.
So like in the particular in the house and truck model, we have assumed that the total number of trucks it remains the same, right? It's not.
Yeah. So the trucks. You're asking about the trucks. The trucks don't rise with age enough to control the damage. So, and if there is a damage where the trucks rise enough, it's not going to be an aging problem. And there's plenty of things like that. That's why it's so specific, I think, what kills you. One.
We say that we add the white noise term, right, which pushes us off the edge at a certain point.
Yeah.
But it also just as well to rejuvenate us.
Yes, yes.
So what is this rejuvenation process?
Yeah. So noise is not only bad because at some point production exceeds removal. This will always happen. If you have more and more damage producing units and the trucks are constant, at some point production exceeds removal. In humans, we think that happens around age 100 and something. But people can live beyond that. Why? Because of the noise. They can be lucky. And their noise they could be here. So, this now, if you're like here, there's not even a steady state. But the noise, you could be here. And so noise can actually keep you alive. It's not only noise, it's also genetics. We'll talk about that. For people over 100, there's a strong genetic signal, and because there's a genetic signal, we have hope that you can make drugs, mimic that lucky genetics.
And it's all modeled in negative noise, which is just as likely as positive noise?
Yeah, and when you think about negative noise, it's like the trucks are on strike a lot. What does that mean? Are little, are not on strike a lot. For example, if you're sleeping 8 hours a day.
Go into a hyper drive.
No, they're low noise. Low noise means like truck is negative noise is like trucks are working more. Yeah. Like that. So sleeping a lot, low stress, low infection. You weren't injured. You didn't break your hip. All these things. It's not, when I say chance, it's like, oh, we have no control. We have a lot of control. It's noise mathematically, but it's something you can deal with.
Something we could hypothetically write down a model for it, but in this model, it's just encapsulated in the noise term.
Yes, the noise term wraps a lot of ignorance in it. But this is like, how you make progress in science, you build biology, physics, doesn't matter. You build simple-minded models, you see what they can do, And if there's a stark contradiction, you need to improve your model. So what we're trying to do in this lecture is test this model in many, many, many ways. And you can never prove it, but the more tests it passes, the more it's a reasonable model for this kind of questions. And of course, we need to understand whether it's histone 3K56 acetylation or histone 4Ka16 acetylation in order to make the drug. That's a more detailed model. We're going to try to work with these different levels. And by the way, when you're a theorist, you do something very perverse. You try to kill your favorite model. Because the more times you don't manage to, the more confident you are. So this model passed many tests. I wanted to tell you about another one, but this is really, at first I want to thank you for the discussion. It's fascinating for me. And we talk with my students. Sometimes after the class, we have new research ideas stimulated by your questions. It's fantastic. In the first lecture, I told you about an experiment where the sins of the past are forgotten. How many of you were the first lesson? And that's an experiment where you do an anti-aging intervention in midlife. I'll remind you though, okay? So this is age, and this is H, the risk of log H, the risk of death. So these are flies on a bad diet, and these are flies on a good diet. You see, they live longer, the risk of death is lower. What happens when we switch diet here? We switch from bad diet to good diet. So the answer is this. Sins of the past are forgotten. Okay. However, if we change temperature, high temperature, low temperature, the slope changes. The risk of the past, sins of the past are not forgotten, only partially forgotten. This is interesting, right? By the way, you do that in flies because you need millions of flies to get the data. Or not millions, lots. And flies are the organisms to do that. Yeah?
Temperature now is temperature, not.
Yeah, it's real temperature, yeah, because they can regulate the temperature. Yeah, it's real temperature, 30 degrees. Or how can our truck model explain an intervention where you quickly lose the sins of the past? And what's the difference between an intervention where you don't forget the sins of the past? Right? This is a puzzle for you. Please parent share and think about that. What does the intervention do to the trucks and houses that can explain that? מה? תשכחי עכשיו את הטמפרטורה. Can you have your attention? Forget about the temperature one for a second. Just think about the rapid one and the shift of diet, okay? From a bad diet to a good diet. How is it so quick? What's going on? Okay. Who wants to say what you came up with? What's going on here in terms of houses and trucks? Yeah.
We thought the amount of garbage is dramatically reduced,
Yeah.
and then it's easier to deal with.
Right. So what does the intervention do? What might the intervention do to make the garbage so quickly reduced? Yeah?
Add more trucks.
Add more trucks.
That's right.
Okay, and that's a possibility, but actually, there's a different answer that's more likely. Yeah?
Change the capabilities of the trucks. Like
Make the trucks better. That'll work. It will work. I think there. Yeah, so I think what's happening biologically is a good diet is like caloric. It's like starving a little bit, and 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 the houses, the cells, they go to conserve, reuse, recycle. They stop growing so much, and they put up more repair. We talked about that. So more repair, especially here, when you're caloric restriction, when you're starved. And so it's in the houses. So the houses make less garbage. What happens in the village if the houses make less garbage? The truck's going to clear and reach a new steady state. It's lower. How long will that take? The fast time scale of the trucks, right? And actually, they're actually less loaded now. So that's what's happening. What about interventions that look like this, where the sins of the past are not forgotten? Houses make less garbage, or more trucks will also do that, like you said. What can do that? So what can do that is, for example, if the main effect is to slow down the rate of building new houses. You don't change the rate where they make garbage or the truck. You just make, from now you have a pretty big village, but it's just going to grow more slowly. So and that's the way you can tell, like with the truck model, what the intervention is doing. So when the fly high temperature, like 30 degrees or 17 degrees, all their metabolism is working less, and it's likely that things like this, the epigenetic alterations, are just happening more slowly. Did I explain myself? And then, actually, also they make less garbage. So in reality, the experiments look a little bit like they drop maybe halfway, and then they have this look. That's what the data really looks like. So it's both less garbage period of time, making less houses. Okay. So here's this experiment actually shows us that there's two time scales in aging, right? Fast and slow. By the way, when you look at Germany, East Germany and West Germany, East Germany is a communist country. West Germany, democratic country. Who was dying more? East Germany. Now you take a cohort of people, and at this age is 1989. The wall fell down. It's the real data. What do you think happened to the East German hazard curve? Hazard curve, risk of death. Is it like sins of the past are forgotten, or like? So the answer is. Is this interesting to you? Is anyone here from Germany? So the data is like this, which means East German risk of death dropped and became because let's say their lifespan increased by 5 years or something. Yeah, we need to explain it, right? But just again, it shows a rapid time scale. It's not as rapid as 1 day in flies, but of course it's very complicated data. And humans is always more complicated, lots of explanations. So I find that this very interesting. Yeah.
Does that mean that the temperature in the German reunification was lower?
Like, so when you say temperature, you mean like noise, right? Not the because the temperature only climate change, but happened later. What does it mean? It means some parameter changed here, and that parameter is interesting to think what it is. And I'm not going to tell you. We're going to deal with it when we talk about the social issues and stuff. It could be lots of different parameters. This fast time scale, in fact, any parameter you change is going to give you the fast time scale change. Slow time scale, you need to change ETA and the rate of house production. So it's a diagnostic. So anyway, that's a way you can test models, right? You can okay. Should we do more? delicious stuff. No, let's not do more delicious stuff. We're going to continue. So we're going to go into the major disease killers and why they rise with age. And we talk more about interventions and molecules, trying to walk math and molecules together. But we have a few more minutes, so we'll maybe really love to hear your questions.
What does building less houses in the body mean?
So one way to interpret it is that the rate of altered stem cells, accumulation of more altered stem cells, is slower, or the rate of more damaged neurons. Yeah.
And you said you were going to talk about the difference between the sexes.
I will talk about the difference between sexes, but not in this. I wanted to get there in this lecture, but discussion was fascinating, so we'll do that. Yeah.
Do all tissues express IL-15 equally, or like different tissues have different amounts, and you might be able to change?
Okay.
Let's say
So this question is about thinking about interventions, right, in a clever way. So the question is, do all tissues express the elixir of life for NK cells equally? So different cell types have different IL-15, but I think it averages out to kind of a constant elixir of life on the first approximation. But I like the way you're thinking. You want to tweak the system, right? By the way, is it better to improve the trucks, make the houses slower, make the houses recycle, increase the experimental? So we need to think about that. We'll think about that too, right? What do different interventions do? They have different effects. I want from people who still didn't ask, to dare to ask. I mean, I love all your questions. Yeah.
Joe's farm is including if you look at the same species but like different sub-creations.
Yeah.
What would change? Noise?
Okay, so if you look at different individuals, genetically different, let's say, in simple like human beings, what changes? So that's again going to be in an upcoming lecture on the genetic basis of aging. And I can say we can rule out things that can't change by much. Otherwise, you have people living to 140. Great question. Yeah.
What do you think the time scale is for pushing you dangerously up the hill, like in terms of being sleep deprived and super stressed?
So the time scale
Full of infections.
of noise, yeah, I would say it's like the trucks. That at least in mice, when I think the trucks, by the way, in mice and humans are quite similar because NK cells. It's not, humans are much, much better at DNA repair, much better than mice. So their rate of building houses is like 40 times slower. Or I would say, not building houses necessarily, but the rate of producing senescent cells, they can get rid of these damaged cells so much better that the rate of making houses times the garbage per house is 40 times slower. So instead of 2 years, you live 80 years. I think that's the main parameter that changes among mammals. But the time scale, so if the trucks are like mice, the time scale of noise should be like days when you're young and months when you're old. And that's the time scale of the fluctuations. Or the time scale of the trucks, which is the time scale that noise has freedom to randomize you. Something like that. So, yeah. If you didn't ask a question in the courses, this is your chance. I want to hear from your precious insights or comments. Yeah.
What's the difference between the recycling and changing the amount of houses in terms of the world?
Yeah. So in terms of models, they're both in EDA. Yeah, but there's a better model you can write where rate of production of garbage has to do with there's irremovable kind of damage, let's say the altered stem cells. They're just produced, that's why they're linear with time. And they produce the garbage. And then interventions that change the rate of building houses affect B. Interventions that recycle affect A. And then you can separate the two parameters. And then it's also what's called a autonomous equation. There's no explicit time in it, which is nice mathematically. And also, maybe from first principles, if you say, give me an equation of aging, but you're not allowed to put time in it explicitly, it has to be whatever. So you can probably derive some of this just from first principles. That's an interesting project. Yeah.
What happens, like, if there is a mechanism that can preserve my stem cells and make them not have, like you said, if I'm starving, then the chances that I will get a problem in my epigenetics is lower.
No,
Right?
I didn't say that. I said that if you're starving, you repair damaged cells better.
Oh, okay.
But if your metabolism is lower, like rate of living is lower, whatever process, I mean, you have to. Maybe I should end with a really hopeful statement, and that was asked before. There is a way, in principle, to reset those epigenetic alterations, go from the core. That way is done every time we were born. It was done because when the human egg is fertilized, it erases the epigenetics. It has to be that way because there's a billion years of doing that. That's why an egg from a 40-year-old woman and a sperm from a 40-year-old man don't make a 40-year-old embryo. They make a 0-year-old embryo. Right? So there's a full reset. Biology knows how to do that. And some of the cutting-edge approaches are trying to do what's called partial reprogramming, which is to do that, but without resetting also the state of our body into embryo, or like, because that is close to cancer, it's a lot of problems. So to take what's called the Yamanaka factors and use only 3 and not 4. So all kind of approaches like that, they show some promise in mice, but there's very early stages. So in principle, there's a way to intervene here, and that biology does. Okay, let's take a nice deep sigh of relief. And see you next week.